In the previous video, we introduced the design curve and what the bending stress distribution ends up looking like as we start to exceed the elastic range and pass the yield point with our loaded conditions. I've already pre-drawn a little bit here. On the left side, I've just redrawn the bending stress distribution diagram. So this is already in your notes from the previous video. On the right, what I've got is I've got a profile view of a beam out to the extreme right. I've kind of drawn it in 3 dimensions just so you can kind of visualize what I'm looking at there. But you can really just kind of scratch out and look simply at the profile view. And then above that, I've drawn the bending moment diagram. Now, as the load increases, the bending moment will just get bigger and bigger and bigger. And there's going to be a point where it eventually crosses that yield moment, the moment that causes the stress to yield. And so where on the beam that intersects that particular location, what we end up doing is that end up being the extents of our any points on the steel beam that is turning where we're starting to get plastic deformation or that permanent deformation. Now the top of this beam in theory will reach a point where we reach the plastic limit, and that means that there's no stress. We can't go any larger with our bending moment because we've gone permanent deformation throughout the entire cross section of the beam. What I'd like to do is compare these back to the different cross sections that I've drawn. The red lines thus far on the far left and the far right represent cross section A. That is the point where the yield stress has reached the equivalent moment value that causes the beam to bend. To go into plastic deformation. So that, again, the yield point. So if you were to look at cross section A, the yield stress would look, or rather the yield stress profile would look like what I've shown in cross section A. Now, somewhere in the middle, where we haven't quite reached the plastic moment yet, that would be the equivalent to cross section B, where the top and the bottom of the beam are going into plastic deformation, but the center of the beam is not. So if I was to draw this right here at the top of cross section A and the bottom of cross section A, we're just barely starting to reach the yield point. But if I look at cross section B, we've actually, nope, get rid of that. We've actually gone a little bit further inward, and all that zone above and below, above the point that I've drawn there, would have reached a permanent deformation state. In other words, it's starting to deform, while the interior of that beam, kind of highlighted with the little circle thing going around there, has not. At cross section A, cross section C, said that wrong, which is the center of the beam where we've reached the plastic moment, the profile would look like it does in diagram C. And that means that the entire top and bottom of the beam has gone into plastic deformation. And so if we were just to kind of connect the dots here, what's happening is we end up with this zone right here along the beam where everything goes into plastic deformation state, and then everything that is not highlighted has still not yet yielded. Now, if this beam has a large load acting on it, and even if it's just the self weight of the beam, which can be significantly heavy, And all of this center zone wants to go into a permanent deformation state. What happens is the beam loses the ability to um, basically sustain its own load, and we end up with what's called a plastic hinge condition. So let me just diagram what this would look like. We'll draw a beam here that is simply supported and under its own load, as long as it hasn't reached that plastic hinge state, then it would stand like that. But if the center of the beam, everything goes into this permanent deformation state, the beam loses its ability to carry that load, and it actually, I'll exaggerate it slightly here, but we actually get this hinge that is created, and the beam will rotate. By rotate, I mean just sags downward as all this material here in the middle permanently deforms under its load. Eventually, it'll hit a point where it starts to hit that strain hardening range. But this is the ideal failure mechanism that is designed for. When we design a steel beam, we're designing for this plastic hinge condition where everything in the center of the beam will go into a permanent deformation state. The beam will sag as shown in the diagram below, and we get what's called free rotation of the beam. That's just a fancy way of saying it sags. And at that point in time, we start to capture our additional strain hardened load. And so long as we don't exceed the ultimate strength that can achieve after strain hardening, the beam looks significantly ugly, but the building doesn't fall down. And this is the condition that we design steel beams and steel columns for. It's a little bit tricky to draw freehand. I'm going to reference you back to the textbook. If you'll see figure 8.43 in the textbook and reread the description there, I think that'll help clarify and tie together this idea of the plastic hinge.